Hello and welcome to this video. This is the last video on geometric progression series. After this we will move on to harmonic progression. So there are 13 problems in this set because I didn't want to make another video for 3 problems. So let's get started. As always, do not look at the solution. First you pause the video when the problem is being stated, and then if you cannot solve it on your own, then look at the solution. Problem number 101 says that if x is equal to sum of a to the power n, where n varies from 0 to infinity, y is equal to sum of b to the power n, where n varies from 0 to infinity, and z is equal to c to the power n, where n varies from 0 to infinity, where a, b, c are in AP such that modulus of a less than 1, modulus of b less than 2, 1, and modulus of c is also less than 1, then we have to show that 1 by x, 1 by y, and 1 by z are in AP. So clearly this is sum of infinite series in GP. So for x we get it as 1 by 1 minus a because our common ratio is a, y is equal to 1 by 1 minus b, and z is equal to 1 by 1 minus c. That is from the formula of a GP for infinite number of terms. So by taking reciprocal, we can write that 1 by x is equal to 1 minus a, 1 by y is equal to 1 minus b, 1 by z is equal to 1 minus c. Now since a, b, c are in AP, 1 minus a, 1 minus b, and 1 minus c will also be in AP, because we know from the property of arithmetic progression, if a number is added or subtracted, the AP remains in AP. Problem number 102 says that given that x with value greater than 0 and less than pi by 4, y having a value greater than pi by 4 and less than pi by 2, and sum of minus 1 to the power k tan to the power 2kx, where k varies from 0 to infinity, is equal to p, and sum of minus 1 to the power k cot to the power 2ky is equal to q, where k varies from 0 to infinity, then prove that sum of tan to the power 2kx cot to the power 2ky, where k varies from 0 to infinity, is 1 by p plus 1 by q minus 1 by pq. So for p we have first term as 1 and r is equal to minus tan square. So p becomes 1 by 1 plus tan square x, which is nothing but cos square x, because 1 plus tan square x is sec square x and 1 by sec square x will be cos square x. For q we have a is equal to 1 and r is equal to minus cot square y. So similarly it becomes sin square y, because 1 plus cot square y will be cos x square y, 1 by cos x square y will be sin square y. So for the final series, we have s is equal to 1 by 1 minus tan square x cot square y. So we change this to cos square x and we change this to sin square y. So the formula now becomes s is equal to 1 by 1 minus cos square x, because tan square x is sin square x by cos square x. So we can write sin square x as 1 minus cos square x. And similarly, cot square y becomes 1 minus sine square y. It should be square y, not sine to the power y, divided by cos square y. So if you solve this, then you get it as pq by p plus q minus 1. Now we take pq to denominator. It becomes 1 by p plus 1 by q minus 1 by pq. Problem number 103 says that an equilateral triangle is drawn by joining the midpoints of a given equilateral triangle. A third equilateral triangle is drawn inside the second in the same manner, and the process is continued indefinitely. If the side of first equilateral triangle is 3 to the power 1 by 4 inch square, it should be inch, not inch square, it is side, not area. Then find the sum of areas of all these triangles. So the area of the outermost triangle will be square root of 3 by 4a square, where a is the side. The sides of subsequent internal triangles will be a by 2, comma a by 4, comma a by 8. So total area would be square root of 3 by 4a square multiplied with 1 by 4 plus 1 by 16 plus 1 by 64, and so on, because your next side would be a by 2 whole square, that is a square by 4. So total area becomes this much, and this leads to this result. So let's verify this. This 1 minus 1 by 4 will become 4 by 3. 4 will get cancelled here. So no, this is wrong. There should be another term 1 for the first one. So root 3 by 4 a square multiplied with 1 plus 1 by 4. There would be 1. So this 1 by 4 won't be there. So it would be 4 by 3. 4 will get cancelled here. A square is nothing but square root of 3. Square root of 3 into square root of 3 would be 3. And then 3 will be in denominator from here. That will get cancelled. And the final result would be 1. I'll correct this before I upload it to GitHub. Actually, I already uploaded it to GitHub. I'll correct and re-upload it. If s is equal to e to the power 1 plus modulus of cos x plus cos square x plus cos cube x plus cos 4x up to infinity, multiply with log of 4 with base c, satisfied the roots of the equation t square minus, it should be log of e, I believe. Log of e, not log of c. Satisfied the roots of the equation t square minus 20t plus 64 is equal to 0. For 0 less than x less than pi, then find the values of x. So what we do is we can rewrite cos square x as modulus of cos square x. So infinite series become 1 by 1 minus modulus of cos x, where modulus of cos x is less than 1. So our sum becomes e is equal to e to the power s log e to the power 4. From logarithm, we know that this is equal to 4 to the power s. Now this satisfies the equation t square minus 22 plus 64. The roots of this equation would be t is equal to 16 and 4, not 16 and 6, 16 and 4. So 4 to the power s, if you compare with 16 and 4, it will give you two results, 1 and 2, which will lead cos x mod of cos x to be 0 comma plus minus 1 by 2. So these three values will give us three results, pi by 2, pi by 3 and 2 pi by 3. Pi by 2 will correspond to 0, pi by 3 will correspond to plus half, and 2 pi by 3 corresponds to minus half. Problem number 105 says that if S is subset of values between minus 1 and minus pi and pi, it denotes the set of values of x satisfying this equation 8 to the power 1 plus cos x plus cos square x plus cos cube x up to infinity is equal to 4 to the power 3, then find the values of x. So similar to previous problem, we can rewrite 4 cube as 8 square, and we convert everything to mod form. So we will have here power of 8 is 2, so the sum would be 2. So 1 by 1 minus mod of cos x is equal to 2, which gives cos x as plus minus 1 by 2. If x is greater than 0 and less than pi by 2, and 2 to the power sine square x plus sine to the power 4x plus up to infinity satisfy the roots of equation x square minus 9x plus 8 is equal to 0, then find the values of cos x by cos x plus sine x. In this case, our infinite series would be, 2 is missing here, sine square x divided by 1 minus sine square x, which is tan square x. So our left hand side is 2 to the power tan square x. Now roots of this is 1 and 8. So tan square x will become 0 or 3. Now x can be 0, x can be plus minus square root of 3. But only x is equal to pi by 3 satisfies the given condition. So now we write cos x by cos x plus sin x as 1 by 1 plus tan x, because we divide by cos x to numerator and denominator. And that's why we have 1 by 1 plus tan x, which is equal to 1 by 1 plus square root of 3. Problem number 107 says that if sum of lambda is equal to 1 by lambda to the power r, where r varies from 0 to infinity, then find sum of lambda minus 1 multiplied with sum of lambda, where lambda varies from 1 to n. So for infinite series, we know that sum of lambda would be lambda by lambda minus 1. Now we substitute this here. So lambda minus 1 will get cancelled and it will remain lambda. The sum of lambda, where lambda varies from 1 to n, is equal to n into n plus 1 by 2. Problem number 100 says that if a, b, c are in AP, then prove that 2 to the power ax plus 1, comma 2 to the power bx plus 1, comma 2 to the power cx plus 1 are in GP for all x not equal to 0. So we divide 2 to the power bx plus 1 with 2 to the power ax plus 1 and 2 to the power cx plus 1 with 2 to the power bx plus 1. So we get b minus a into x is equal to c minus b into x, which implies that b minus a is equal to c minus b for all x not equal to 0. So clearly we can see that a, b, c are in AP. If a plus b to the power x divided by 1 minus b to the power x is equal to b plus ce to the power x divided by b minus ce to the power x is equal to c plus de to the power x divided by c minus de to the power x, then prove that a, b, c, d are in GP. So we rewrite a plus b to the power x as 2a minus be to the power x. So we get the equality as 2a divided by a minus b to the power x minus 1 is equal to 2b by b minus c to the power x minus 1 is equal to 2c by c minus d to the power x minus 1. Now we remove all this and we remove 2 and take reciprocal. So we get the result as a minus b to the power x by a is equal to b minus c to the power x by b is equal to c minus d to the power x by c. So now we divide, we get 1 minus b by a e to the power x is equal to 1 minus c by b e to the power x is equal to 1 minus d by c e to the power x. So we can remove 1 and then we can remove ex, which gives us b by a is equal to c by b is equal to d by c. And thus we can say that a, b, c, d are in GP. If x, y, z are in GP and tan inverse x, there should be a space. And tan inverse x, tan inverse y, tan inverse z are in AP, then prove that x is equal to y is equal to z, but their common values are not necessarily 0. So given that x, y, z are in GP, y square is equal to xz. Now tan inverse x, tan inverse y, and tan inverse z are in AP, so we write 2 tan inverse y is equal to tan inverse x plus tan inverse z. Now this is equal to 2y by 1 minus y square is equal to x plus z by 1 minus xz. Now y square is equal to xz, so we can cancel out the denominator part, resulting in 2y is equal to x plus z. We square this and we get x minus z whole square is equal to 0, which implies x is equal to z. And that's why x is equal to y is equal to z. Problem number 111 says that if a, b, c are three unequal numbers such that a, b, c are in AP and b minus b minus a, comma c minus b, comma a are in GP, then prove that a is to b is to c is equal to 1 is to 2 is to 3. We are given that b minus a is equal to c minus b because they are in AP. Now c minus b whole square is equal to a into b minus a because b minus a, c minus b and a are in GP. So we substitute for c minus b as b minus a, we get b minus a whole square is equal to a into b minus a. We cancel out b minus a and we get b minus a is equal to a, that is b is equal to 2a. Now we substitute this for c. So c is equal to 2b minus a. Now where did we get this? So you can have this value where you can substitute this. So c is equal to 2b minus a, 2b is equal to 4a, 4a minus a is equal to 3a. So a is to b is to c is equal to 1 is to 2 is to 3. Problem number 112 says that the sides ABC of a triangle are in GP such that there is spelling mistake such that log of a minus log of 2b, comma log of 2b minus log of 3c, comma log of 3c minus a are it should be log of a are in AP, then prove that triangle ABC is an obtuse angle triangle. We are given that log of a by 2b, comma log of 2b by 3c, comma log of 3c by a. Subtraction which we have converted into fractional form of log. So these are in AP, so we can say that 2 into log of 2b by 3c is equal to log of a by 2b plus log of 3c by 2a, 3c by a. So we multiply the right side and then the power 2 will come here and we take anti-log. We get it as 2b by 3c whole square is equal to 3c by 2b. So here A will get cancelled. Now we see this. So here what we have is 8b cube is equal to 27c cube, which gives us 2b is equal to 3c. Now we are also given that ABC are in GP, so b square is equal to AC. Now we substitute for b, we get 9c square by 4 is equal to AC. That means A is equal to 9 by 4c. Now we convert the value of b, which is 3c by 2, to same denominator which is for A, that is 4. So sides are 9 by 4c, 6 by 4c, comma c. So clearly A is our greatest side, and then we find the corresponding angle, which is A. So cos A will be b square plus c square minus a square by 2bc is equal to minus 29 by 48, which is less than 0. And that is why angle A would be an obtuse angle triangle, because cos A is negative if only, not only, if it is greater than pi by 2. So angle A will be obtuse angle. Problem number 13 says that if the roots of the equation ax cube plus bx square plus cx plus d is equal to 0 be in GP, then prove that c cube A is equal to b cube d. So we take the roots as p by r comma p comma pr. The product of roots will be p cube, which will be equal to minus d by a. This formula comes from theory of equations. So we can write this as ap cube plus d is equal to 0. Also, the p here will be a root of the equation. So we can substitute x with p. That is ap cube plus bp square plus cp plus d is equal to 0. Now we already have ap cube plus d is equal to 0. So this becomes bp square plus cp is equal to 0. Now we remove p here, so we get bp is equal to minus c. Now this implies that b cube p cube is plus c cube is equal to 0. So we substitute for p cube again, and we get the result. So with this we come to the end of our tutorial or practice with geometric progression. And in next slide I'll start harmonic progression. There is not much of theory with harmonic progression, so we'll solve the problems as well in our next video. If you have enjoyed and found this video useful, then please subscribe to the channel and like the video, because that keeps me motivated for making more videos. Thanks a lot for watching the video.